Hello, we are Beyond Robotics, the first Greek team participating in the European Rover Challenge. Our team is under the affiliation of the National Technical University of Athens and is composed of 70 university students and young graduates with backgrounds in mechatronics, computer science, geology and other fields. In this video, we proudly introduce the result of our 2-year effort to design and build our first space rover, Talos, for the ERC 2023.
Our rover is a complex system designed to meet the requirements of the competition. It is divided into 7 subsystems, each with a different role. The development process that we followed is similar to the methodologies used in the space industry. We broke down the project into phases, starting from the conceptual, preliminary and detailed design up to manufacturing, assembly, integration and testing. By following system engineering principles, we set requirements for the rover and subsystems, manage risks, and prepare testing campaigns to verify the functionality and performance of our system.
Our mobility system consists of a 4-wheel bogie suspension and differential bar. The system also uses 4 brushless DC electric motors reaching up to 35 Nm torque each. These motors were selected through kinematic analysis, always keeping in mind the performance criteria in order to navigate the ERC Mars Yard as well as the restrictions of commercially available products. Moreover, skid steering is used for the rover's maneuvers and navigation. All the mechanical parts of the mobility system were designed and simulated by the team through an iterative process using 3D design software and FEA. Finally, the manufacturing, assembly and integration of the mobility system were done by the team in our small yet efficient lab in Athens.
The structure subsystem is responsible for the design of the rover chassis and the effective payload configuration. Our robust and lightweight chassis consists of an aluminum frame and side panels. These two profiles ensure a high level of modularity and load-bearing capacity, while aluminum panels, weather protection and heat dissipation. We use static and dynamic finite element analysis simulations for the evaluation of the platform's structural integrity and the optimization of the design. Finally, to facilitate all the equipment correctly, 3D printed mounted parts were designed and manufactured. The energy storage system is a parallel circuitry of 2 lithium-ion batteries. Each pack has an embedded BMS for self-balancing and battery protection. To provide power for every subsystem in the appropriate voltage level, some high-efficient converters are used. A voltmeter and ammeter in all subsystems have been placed in combination with a dedicated microcontroller for energy monitoring. Utilizing this data, the total and per subsystem energy are calculated by the Saturn computer. The rover includes 2 safety systems. Firstly, the isolation emergency system. This isolates the battery packs from the rest subsystems, so when it is activated, the power supply of all systems stops. Secondly, the moving parts emergency system. This is similar, but it stops only the operation of the moving parts, deactivating the rover motors. For this system, there also exists the option to be activated remotely.
For the main computer of the rover, we chose a small form factor PC based on Ryzen architecture running Ubuntu. For peripheral interconnection and redundancy, we used a companion Raspberry Pi. We developed our own APIs based on Python and C++ programming languages. Data from sensors are stored in a time series database and visualized. We control the rover via a gamepad and developed an Angular web application for friendly human-robot interaction.
We use an extended Kalman filter to fuse data from visual odometry produced by a camera and an IMU. Also, we use a SLAM algorithm combining 2 cameras for accurate localization and mapping. Detected Aruco markers are used during the SLAM process. A 360 camera captures video for post-analysis of the environment. We estimate the traversability of the terrain online in order to navigate effectively and avoid obstacles. The a priori map given by the competition is used for high-level planning.
The telecom subsystem is responsible for the telecommand of the rover and its telemetry with the base station. For our setup, we used 2 Ubiquiti U6 Pro access points and 1 TP-Link router to simulate the DHCP services. We expect to provide dual-band connectivity in an omnidirectional level with high data rates while we keep the default internal antenna of the access point. Based on that, we tested our communication link in both line of sight and non-line of sight environments, while we also created some interferences such as reflections, fadings, and co-channeling.
The responsibility of the mechanical subsystem was developing the robotic arm and the sample storage system. The robotic arm is constructed with 3D printed plastic components and uses geared stepper motors for the movement of all its axes. We are very proud of the tool changing system that allows the arm to change tools autonomously. The tools include a parallel gripper, a drill, a voltage measuring probe, and a depth gathering scoop. The sample storage system is also made with 3D printed components and acrylic plastic sheets. The samples are gathered in a carousel system and a rock container.
The main objective of the science subsystem is to understand and interpret the geological history of the Mars yard using drone images and surface samples we collect with our rover. To that end, we have brought together a diverse group of scientists that includes geologists, remote sensing experts, and engineers.
As for our drone, due to time constraints, we chose a DJI Mavic Air, and for its control, we developed a custom app allowing autonomous navigation using waypoints.
We are also developing a unique and innovative microscope and grain collection system to perform petrographic and shape analysis of rock and mineral fragments using polarized and structured light. The grains are collected on an adhesive tape, which will be also storing those grains for sample return.
We first presented our kit to the public in October 2022 with the support of the Hellenic Space Center, the Ministry of Digital Governance, and the Space Cluster of Coralia. Beyond Robotics operates under the auspices of the Prefecture of Attica and of the National Technical University of Athens. We are close to the student community by participating in robotics and science festivals like the Robotics Festival of the Municipality of Piraeus, trying to inspire the new generation to engage in space and robotics projects. Our biggest thanks goes to our sponsors and especially to our biggest donor, Bodosaki Foundation. A big thank you to our donors from our crowdfunding campaign as well.